everyone, what's up? Welcome back to my tutorial channel. Today I'm back to make tutorial lesson in probability and SMP preparation. And the lesson today I will be covering is frequently used discrete distribution. In the lesson today I will be considering the 7 most basic distribution in discrete case. So the first distribution is uniform, then binomial distribution, Poisson distribution, geometric distribution, negative binomial distribution, hypergeometric distribution, and multinomial distribution. So let's get started with the first one. Uniform distribution on endpoints. The terminology uniform mean like any point here is treated equally. So the probability function of a random discrete variable x that follows uniform distribution is p of x is 1 over n for any point from 1 to n, any integer from 1 to n, and the probability is 0 in any other point. The mean of x is e of x is summation x times p of x, and this is summation of x over n. So expected value of x is n plus 1 over 2. And the variance of x is ex squared minus ex whole square. So the variance of x is n squared minus 1 over 12. This is using the techniques we learned from the last lesson, how to compute the average, the expectation, and the variance. So for any distribution, you really need to ask yourself 5 questions. The first question, what is the probability function? The second question, what is the mean? The third question, what is the variance? Question number 4 is when to use this. And question number 5 is the moment generating function of this distribution. So for the moment generating function, I'm going to talk about this after we finish the 7 distribution. So uniform distribution is used when we have n points that are equally treated. So here we have n point from 1 to n, and the probability of getting any point here is the same. So the probability at any point from 1 to n is 1 over n, and any points outside this range is 0. So that's the first distribution. Now we look at the second distribution, binomial distribution with parameters n and p. So a trial, or as we say a Bernoulli experiment, is a single experiment results in either success or success with probability p, or failure with probability 1 minus p, which is q. So a trial is basically just like any experiment that results in either success or failure. For example, you play a game with your friends, so either you win or you lose. You win means a success, and you lose means failure. And if there are n independent trials conducted, and let x be the number of successes that occur, then x is said to follow binomial distribution with parameters n and p. The probability function is p of x equal to n to x, p to the x, 1 minus p to the n minus x. The mean of this random variable is np. This formulas can be proved by the technique summation x times p of x. And to derive the formulas, we have e of x is n times p. And the variance of this random variable is var of x equal to n times p times 1 minus p. So this was about binomial distribution. Now the third distribution is Poisson distribution with parameter lambda. The probability function of this distribution is p of x equal to e to the negative lambda to the x over x factorials, and x can be any number from any integers from 0, 1, 2, 3, and so on. The mean of this distribution is lambda and the variance is also lambda. We can prove it by the techniques using summation x times p of x and derive the formulas. The application of this distribution, Poisson distribution, is used when counting numbers of events in a certain period of time. For example, the number of customers arrive in a bank in an hour period. So if we are given a period like an interval of time and we want to count how many times an event occurs, then that is an application of Poisson distribution. So I repeat, for any distribution, ask yourself 5 questions. Where is the probability function? Where is the mean? Where is the variance? When to use it? And where is the moment generating function? Next distribution, geometric distribution with parameter p. So it looks similar to binomial, however, we modify it a little bit. So again, a single trial of an experiment results in either success with probability p or failure with probability 1 minus p. 1 minus p. The experiment is performed with successive independent trials until the first success occurs. So this is the difference between geometric distribution and binomial distribution. For binomial distribution, we perform a fixed number of independent trials. That means the number of independent trials given, and we define the number of success. But here in geometric distribution, we don't know how many times we have to perform the independent trials, but we are keep performing the trials until we got the first success. So let's x be the number of failures until the first success occurs. So x here is the discrete random variable that follows geometric distribution. And the probability function of x is p of x is 1 minus p to the x times p. Because until the first success we have, suppose x is the number of failures. So until the first success, that means the total trials we conducted is x plus 1. So the probability of p, the probability of x is 1 minus p to the x, because the first x trials are fails and the last trial is success. So we have 1 minus p to the x times p. And the mean and the variance of x is e of x is 1 minus p over p, and variance of x is 1 minus p over p squared. So this is these two formulas can be proved using the technique summation x times p of x and should derive the formulas. So that's what about geometric distribution. But here, the study is conducted until we have one success. Until one success, the first success occurs. And in some cases, we not only consider only one success. We might have question how the study is conducted until we have maybe k successes. So let's look at the next distribution, negative binomial distribution with parameters r and p. So this is the reverse problem of binomial distribution. This is a negative binomial distribution with parameters r and p. So it looks similar to geometric, but the only different ways we conduct the experiment until we have r successes, not only one. So a single trial of an experiment results in either success with probability p and fail with probability 1 minus p. And the experiment is performed with successive independent trials until the rth success occurs. Let x be the number of failures until the rth success occurs. So x here is this discrete random variable that follows negative binomial distribution. And the probability function is p of x equal to r plus 1 minus 1 choose x, p to the r, 1 minus p to the x, because x is the number of failures. So until we have r success, the first we have x failures, and r plus x minus 1 success, and then the last one is success. So we have r plus x minus 1 choose x, and p to the r 1 minus p to the x. And the mean and the variance of x are e of x is r times 1 minus p over p, and variance of x is r times 1 minus p whole square over p. So this looks similar to geometrics, but the only thing is r here is not 1. So if r is 1, we have geometric distribution, because if r is 1, p of x is x choose if r is 1, then actual x is 1. P to the r is p. 1 minus p to x, this is just basically p times 1 minus p to the x, and this is exactly geometric distribution. And e of x is 1 minus p over p, because r is 1, and variance of x is 1 minus p whole square over p. So if r is 1, negative binomial distribution becomes a geometric distribution. So geometric distribution is a special case of negative binomial distribution. That is when r is 1. Next, hypergeometric distribution with integers parameters m, k, and n. So in a group of n subjects, there are k subjects of type 1 and n minus k subjects of type 2. If a group of n objects are withdrawn at random without replacement from n subjects, and let x be the number of type 1 in the chosen subjects. So x here is the discrete random variables that follows a hypergeometric distribution with integer parameters m, k, and n. And probability of x is basically k choose x times m minus k choose n minus x over m choose n, because the number of ways to choose the n group such that we have x from k, x from type 1 and n minus x is from type 2 is k choose x, n minus k choose n minus x, and the number of total way to withdraw n subjects from m subject is m choose n. So the probability of x is k choose x, n minus k over choose n minus x over m choose n. The mean and the variance. So mean of this distribution is nk over m. We can just derive the formulas using summation x times p of x, and it's gonna be a long way, but the final result is e of x is nk over m, and variance of x is nk m minus k m minus n over m squared m minus 1. So this is about hypergeometric distribution. So in this lesson, uniform distribution is easy to remember. Binomial distribution is easy to remember. However, you might be confused among geometrics, negative binomial, hypergeometric distribution. So to pay attention on these. Poisson is easy. Poisson is used when we are given an interval of times, and the question asks for the number of times an event occurs in during that interval of time. The last distribution looks similar to binomial distribution, but we consider more than 2 possible outcomes. So multinomial distribution is the general case of binomial distribution. Suppose that an experiment has k possible outcomes. So here we have k possible outcomes, not only 2 success and failure, we have k possible, with corresponding probability p1, p2 to pk. If the experiment is performed in successive times independently, let xi be the number of experiments that result in outcome I, so that x1 plus x2 plus plus xk is n. The multinomial distribution function is p of x1 equal to little x1, x2 is equal to little x2, xk equal to little xk. And this is n factorial over x1 factorial, x2 factorial, xk factorial, p1 to x1, p2 to x2, pk to xk. So that was everything about the 7 important distribution in discrete case. Now we are going to consider the last thing in this lesson, the moment generating function. So because I said for any distribution, you have to ask yourself 5 questions. The first question, what is the probability function? Second question, what is the mean? The third question, what is the variance? Question number 4 is when to apply that distribution. And the last question, a moment generating function. Because sometimes, it's really hard for you to derive the formula of variance and expected value and some moment. So moment generating function is sometimes very useful to compute the mean, the variance. For discrete uniform, the moment generating function is e to the t times e to the nt minus 1 over e to the t minus 1. For binomial, is 1 minus p plus p to the p times e to the t, the whole thing to the power n. Poisson, moment generating function is e to the lambda times e to the t minus 1. For geometric, is p over 1 minus p et. Negative binomial is p over 1 minus p e to the t, the whole thing to the t. And the hypergeometric is nk m minus n over m squared m minus 1. To prove these formulas, we basically follow the old techniques from the last lesson. The moment generating function is expected value of e to the tx, and we derive these formulas. For discrete, we use summation. For continuous, we use integral. So again, for any distribution, ask yourself 5 questions. What is the probability function? What is the mean? What is the variance? When to use it? And what is the moment generating function? If you don't remember the moment generating function, then start with this lesson. Start with how we compute moment generating function to remember expected value e to the tx. And here among these distribution, you really need to focus on discrete, uniform, binomial, Poisson. The rest usually is not really important because on the exam, like, we don't usually we just have question that focus on discrete, uniform, binomial, and Poisson. So pay attention to the first 3 distribution. The last 3 distribution, you should also study them, but these 3 will not be on the test. It could be, but not often. Like, we might have maximum 1 question. Okay, so that is everything about today's lesson. Now we are going to practice the first problem. A company price is hurricane insurance using the following assumption. In any calendar year, there can be at most 1 hurricane. In any calendar year, the probability of hurricane is 0.05. This is 0.05. The number of hurricanes in any calendar year is independent of the number of hurricanes in any other calendar year. Using common assumption, calculate the probability that there are fewer than 3 hurricanes in a 20 years period. So here we have the number of hurricanes in any years is independent with the number of hurricanes in any other year. So each calendar year is considered to be a trial. We have either success or failure. We have 2 positive outcomes. Either we have hurricanes or not having hurricanes, because in each year we have at most 1 hurricane. We're not going to have 2 or more. Should either have no hurricane or 1 hurricane. So only 2 possible outcomes in each trial. And here we have 20 years. That means we have 20 trials. So this is an example of binomial distribution. So notice, each calendar year is a trial. And the number of hurricanes in 20 years is binomially distributed with P is 0.05 and N is 20. So probability of fewer than 3 hurricanes in 20 years period is P of 0 plus P of 1 plus P of 2, and follow the binomial of distribution formula. We have the answer is 0.9246, so E is the answer. So now we are going to problem number 2. An actuary has discovered that policyholders are 3 times as likely to file 2 claims as to file 4 claims. If the number of claims filed has a Poisson distribution, what is the variance of the number of claims filed? So remember, for a Poisson distribution, P of x, the probability function is e to the negative lambda, lambda to the x over x factorial. And the variance of this distribution is just lambda. So to find variance, basically we have to find lambda. So we are going to use one piece of information that's given here. An actuary has discovered that policyholders are 3 times as likely to file 2 claims as to file 4 claims. So that means P of 2 is equals to 3 times P of 4. And using this formula, we have e to the negative lambda, lambda squared over 2 factorial is equal to 3 e to the negative lambda, lambda to the 4 over 4 factorial. So here e to the negative lambda and e to the negative lambda is cancelled. Lambda square with lambda square cancel. On the right hand side we have lambda square. 3 with 4 factorial, 2 factorial with 2 factorial it cancel. We have 3 times 4. 3 with 3 cancel, so we have 4 on the right hand side. So we have 1 over 2 factorial, 3 times lambda square over 4 factorial, and lambda square is 4. So lambda is 2, and variance of x is lambda, which is 2. So D is the answer. Next. So now we're going to work on problem number 3. A study is being conducted in which the health of 2 independent groups of 10 policyholders is being monitored over a 1-year period of time. Individual participants in the study drop out before the end of the study with probability 0.2 independently of the other participants. What is the probability that at least 9 participants complete the study in one of the 2 groups but not in both groups? So here we have 2 groups, and the question is, what is the probability that at least 9 participants complete the study in one of the 2 groups but not in both groups? So we are going to consider the 2 groups separately and then combine them. So in each group of 10 policyholders, the number of individuals complete the study is binomially distributed with n is 10 and p is 0.8. So in the first group, probability of at least 9 complete the study is p of 9 plus p of 10, and using binomial distribution formulas we have 0.3758. And the probability of less than 9 completes is just the complement event of at least 9 complete, so we have 1 minus 0.3758, which is 0.6242. And similar for group 2, everything would be the same. And now we look back to the question, what is the probability at least 9 participants complete the study in one of the 2 groups but not in both groups? So that means like either group 1 at least 9 complete and group 2 less than 9 complete, or in group 1 less than 9 complete and in group 2 at least 9 complete. So we have 2 cases. So we combine the 2 cases. We have probability that at least 9 participants complete the study in one of the 2 groups but not in both groups. So probability of at least 9 complete in group 1 is 0.3758. Probability of less than 9 complete in group 2 is 0.6242. And the second case is less than 9 complete in group 1, so it's 0.6242. And at least 9 complete in group 2 is 0.3758. So the answer is 0.469. So the answer is E. Problem number 4. A hospital received 1/5 flows vaccine shipments from company X and the remainder of its shipments from the other companies. Its shipments contains a very large number of vaccine vials. For company X, 10% of vials are ineffective. For every other company 2% of vials are ineffective, the hospital tests 30 randomly selected vials from a shipment and finds that one vial is ineffective. What is the probability that this shipment came from company X? So here we have one event has already been occurred, and we need to find the probability of the other event. So the event that among 30 randomly selected vial shipment, one vial is ineffective is already occurred. So we are going to call X is the event that the shipment is from company X, and let's Z is the number of vial in the 30 vials that is ineffective. So let's X be the event that the shipment is of company X, and Z be the number of ineffective vials in the shipment. So the question is basically asked us to find probability of X given Z equal to 1, because that's the question asks for what is the probability that this shipment come from company X, given that the hospital tests 30 randomly selected vials from the shipment and finds that one vial is ineffective. So using conditional probability, we have this probability X and Z equal to 1 over probability Z equal to 1, and the numerator is basically just know that the shipment from it's just basically the probability that the shipment is from X, and there is only one vial is ineffective. So it's 1/5 times 30 choose 1, 0.1 times 0.9 to the 29. 1/5 is the probability that the shipment come from company X, and 30 choose 1, 0.1, 0.9 to the 29 is the probability of one vial is ineffective. And probability of Z equal to 1 using total probability formulas. We have probability of Z equal to 1 given X times probability of X plus probability of Z equal to 1 given X prime times probability of X prime. So the answer is 0.096. So that's about problem number 4. Now we go to the last problem today. Let's X be a random variable from with moment generating function. mxt is 2 plus e to the t over 3, the whole thing to the 9. Calculate variance of x. So this is a moment generating function. Remember the variance of x is ex squared minus ex. Ex squared is the second derivative of moment generating function at the point t equals to 0, and e of x is the first derivative. So we calculate the first derivative, d over dt of mt and substitute 0. We have e of x is 3, and ex squared is the second derivative, so is equal to 11. This is calculus. This is acknowledged from calculus. You have to you should at least know how to differentiate, take derivative of the function. So ex is 3, ex squared is 11, so the variance of x is ex squared minus ex whole square, so 11 minus 3 squared, which is 2. So 2 is the variance of x. That's problem number 5. So that is everything of today. Thank you so much for watching. I hope you guys enjoy. So next video, I'm gonna talk about some frequently used continuous distribution. And here, by the way, I introduced the textbook I used to compose this video, and also to give you a recommendation for people who want to practice for exam P. So this is a textbook, Text Study Manual, SOA Exam P, CAS Exam 1, 2009 edition. You can get the later edition if you can, but I think 2009 is good enough. The author is Samuel Pruverman, PhD ASA. Alright, thank you so much. Bye.